Okay, so I think we'll start now. And so, hi everyone. Please, we encourage all of you to set your cameras on. It's a thing that helps us communicate better. And hope everyone is well. And in our meeting today, we're going to do our first step in the world of deep learning. And I'm not sure how excited you are, but I'm kind of excited because we'll try today to demystify this thing called artificial neural networks and understand the way they work. I'll just ask everyone to mute yourselves, please, unless, of course, you want to ask a question. And let us start. So, oh yeah, first, one thing about the logistics. So about your homework, it's important that when you submit your homework, please do it with the outputs in the notebook, so that you run everything and you get the outputs written there in the notebook. And then this file is what we want you to send us, so we'll be able to grade it better. Okay, so let me just remind you one observation that we had in the last time we met. It was 2 weeks ago. And so we were talking about this thing called feature transform. So we were dealing with linear regression, and then in the tutorial you learned about the softmax classification or logistic regression. And we said that what we can do is to have our input transform by the feature transformation to this. I'm sure you all remember that we used this observation to actually perform a polynomial fitting in the last time we met. So we used these polynomial features here, and then linear hypothesis there, and now we were able to have this. But what we're after today, and this is in many ways the greatness of neural networks, and so what we're after today is to have this feature transform learnable. Okay, so that actually we want to learn how to transform our input data. Simple linear action we're going to take at the end of the stream is going to be highly influential, very expressive, and able to do really important stuff. And the greatness is actually here at this point here, where we have this representation, because everything that comes after here we've already seen, we've already done. Okay, so at this point we're going to use softmax classifier for classification usually, or we're going to use linear regression from some kind. Sometimes it would be different stuff, but it's going to be very simple. And the true greatness, and the place where we look at later and analyze and see that we get these really wonderful things, is right here, is the representation that we get after this transformation. And moreover, the process itself is going to be made of many representations followed one by each other. And this is in many ways inspired by actually the human brain. This is hierarchical representations of the input that we get until we get this almost final representation that we're going to use for the final task of classification or regression or whatever we want to do. So let's talk about artificial neural networks. And usually in many courses that teach deep learning and artificial neural networks, at this point comes some slides about neuroscience. And this is a thing that we're not going to do. I'm not a neuroscientist. And actually the thing is that artificial neural networks are only vaguely inspired by biological neural networks. So while it is extremely helpful for the fathers of deep learning to be aware of neuroscience facts about the human brain or animal's brain, for us, we're going to accept the fact that it was inspired by this, but we're going to go directly to the algorithms, to the mathematics of how these things work. We're going to drop some clues to things that are inspired by neurons in the human brain. So here is how things are going to work. So we're going to have an input vector, and we eventually want to get an output vector. And the sizes can be anything that we want, okay? And in an artificial neural network called hidden layers, and we're going to have as many of them as needed. And the number of neurons and the number of layers that we have is sort of a hyperparameter. It's a design choice that is called the architecture of the neural network. Okay, so it's not something that is learned. Before you begin any process of learning, you as a researcher, developer, engineer, whatever you are, you decide on the architecture that you're going to use, how many layers and how many neurons in each layer. So each such circle that you see here is called a neuron. And we're going to annotate them so that you see, we actually look distinctively at the first layer, this layer 0, because this is the input. But in almost any other term, it's not. It has nothing special with respect to the other layers, and you can see how the annotation works. So each such neuron, I'm going to annotate them by X, and you can do whatever you want. If you look at many books, everyone has its own way to annotate. We're going to annotate the neurons with X. So each such neuron X has a superscript indicating the layer it belongs to, and a subscript that indicates the ordinal number of the neuron inside this layer. So layer 0 is the input, and then we have all these hidden layers numbered, and we have a capital L for the output layer. So this is like the first element of an artificial neural network. The first element is the neurons. The second element is called weights. Okay, so these are these arrows that you see here connecting, and between every two neurons from adjacent layers, we're going to have a connecting weight. Each such weight has a value, and for example, we can annotate this weight you see here in red. So we will call it W with subscript 1, and superscript 1, and the superscript is 1 because this weight belongs to the layer of weights that creates the neurons of layer number 1. Okay, so this is superscript 1. This is in the scripts 1 and 3 connected to in the forward side of the arrow, and the second one is where we came from, which is in this case the number 3. And you may be asking yourself, also here there was like many other ways to annotate this. Sometimes some people do it the other way around. They would do 3 and then 1, and maybe you can guess by yourselves why this is the way I choose to annotate. And so this is, we're going to regard this all these layers, all these weights in this layer, and we're going to regard them as a matrix. Okay, and it will be really easy. I'm sure most of you can see this by now. It will be really easy to say what are all the neurons in this layer with respect to this just by multiplying the matrix. So this saves us from transposing the matrix more or less. Okay, so each such weight has a value, and these weights are going to be the parameters. These are the things we're going to change while we are training. Okay, so a basic neuron, in a basic neural network, everything is going to be frozen. The number of neurons, the number of layers, etc. The only thing that changes while we train is the values of the weights. So you can say that in terms of okay, so can you all mute yourselves?
Tyler wanted to buy like 50 plates. I need to keep forgetting to bring one for it. What did you think of that proposal?
Okay, so in terms of hypothesis class, so the hypothesis class is determined per a neural architecture. So we have this architecture with so-and-so layers and neurons and whatever. And now we have the hypothesis class actually includes all the hypotheses that are this specific network, but with all possible values for all the weights in the network. So far, are we okay? Is everything clear? Can we go on? Okay, great. I encourage you to, from time to time, I'm going to ask you if everything is clear. So virtual or real thumbs up would help me see that. And also, if you have questions, please ask me. All right. So let's see the math of this neural network, how everything is defined. So every such neuron, every such neuron is actually a function. Okay, and we're going to define how this function is actually applied to the neurons of the layer. So, okay, so if we take as an example this neuron layer number 1 over here, and want to check this function. So we're going to define it this way. So it's going to be a function of all the neurons in the layer that in one layer to the back. And the way we're going to first define it is this summation over the multiplication of all the weights with all the matching neurons. So this is a linear combination of the neurons of this layer, okay? But this linear combination uses these learned weights, okay? So each neuron with its own weight. But we're also going to add this bias term that is also a learned parameter, okay? And each neuron has its own learned bias term. And finally, we're going to do one more thing. So we're going to take this linear, or if you also look at the bias, it's an affine expression. And we're going to apply another function, which is a non-linear function called an activation function. And this activation function can be whatever you want it to be, but there are some common activation functions that are used a lot. So one of which you already know, you've already seen in the tutorial. It's called sigmoid. Okay, so like tangent. So actually, I'm sure most of you know that a hyperbolic tangent is almost the same as a sigmoid. You just shift it a bit and stretch it a bit. You can see by the function. And the more recent one, it's from 2011 actually, and a very, very simple one, and usually the one that is used the most, is called ReLU. ReLU stands for rectified linear unit. And as you can see, it's one of the most simplest functions you can actually think of. It basically just says that if its input is negative, then make it 0. Otherwise, don't do anything, just have it as it is. Okay, so these are 3 options that are very common, but you can do, there are many other stuff that you can do. It's important for this sigma function over here, this activation, to be non-linear. Okay, so this is how a single neuron is defined as a function of the neurons that from the layer before. But we should also be more efficient and to think about a neural network in a vectorized way. So another thing we can do is we can say that each layer of neurons is actually a vector. And then each set of weights of each layer can be regarded as a matrix. Okay? And this way, we can take the same equation that we have here, the same function that we have here, and now express it in a vectorized way. And this is how it's going to look. So you see, these are all vectors and matrices now. And let me just clarify a few things. So we have this vector X super L, and this is a function of a vector that was before. For example, X super 1 can be a function of X super 0. And you can see that we have the matrix multiplication, which is exactly equivalent to this summation that you see over here, plus a bias vector this time. So the bias vector is the vector of biases for all the neurons in the output layer, in the layer numbered L. And finally, you can see that we apply the activation, but you see the activation is also in boldface here. So this is my way of indicating that this is now regarded as a function of a vector that returns a vector, and it's actually super simple. It just works pointwise. So it just says that you get a vector, and each element of this vector is now we're now going to apply this simple scalar nonlinear activation separately. Okay, and so finally, how this thing works. So from start to end, when you get some input, then you apply it in, and then all the neurons gradually get their values until we get to the output layer. So this is how the network works. You need to assign values to the neurons layer by layer. Okay, and these can be many layers. So I have now one question for you, and my question is, why do I need the nonlinear activation? Why would that help me? Why am I indicating that it has to be nonlinear? Any ideas?
Linear, it collapses to one layer, no?
Right, exactly. So what Jonathan is saying is true. So think about it. If I have no activations, no nonlinear activations, then due to the associativity of matrix multiplication, so the entire network would be expressed possibly just by a single matrix multiplication. And the whole thing that we have here wouldn't be a network anymore. It would be just a very complicated way to do linear regression. Okay, or a logistic regression or a softmax classification. Having this nonlinearity between the linear layers makes our hypothesis much more complicated, much more expressive, and a whole different thing that we cannot collapse to just a linear function.
It's even
Okay,
if
yeah.
Assaf?
Yeah.
Even if you have the B parameter in every weight, because it's not as if you would write a sequence of matrices and just multiply them. It's a little bit
Right. The bias, that's true. The bias changes it. So at each layer, so it's going to be a set of affine functions, and eventually it's going to be an affine function.
okay.
Okay. So it's not going to be linear, right? We should do this distinction. It's going to be affine. So it's linear plus bias at the end also.
Okay, but eventually it will be just one affine function.
Yeah. Yeah. Okay, so just to go back to what we wanted to achieve. So now you can see that all these layers until the almost last layer, they are our feature transform. So we take the input vector, and each time we apply a layer, we get a new representation for the input that we have. So the first layer gives us one representation, and so on until we get to this L-1 representation. This is a way to represent our data. And once this whole process is going to be a learned process, then what we can say is that this representation is a learned representation that represents the data best to the task that we want to perform. So if we want to perform a linear classification here at the end, so we have a good reason to believe that if everything works well, then the data is represented in this layer such that there is good linear separation between the classes, for example. Okay, so in this way we achieve what we actually wanted to achieve. And the true greatness is here, is the feature transform. The end, as pointed out before, is usually very simple. And I have another question for you now. So what would you call a single layered network? If I tell you that I'm going to have just a network with a single layer, how can you name that? Any ideas? No? Quiet today. So I'll try to help you. So if you have just a single layer, we only know feed-forward networks in this phase in where we are. With sigmoid activation, for example, then this is exactly logistic regression. And if you have a single layer with MSE loss, then this would be exactly linear regression. Okay, so the neural network actually just say that we add these hidden layers, and this is the representation learning that I'm talking about all the time.
Assaf,
okay.
Question.
Yeah. Yes.
What we did in the homework was a softmax function, and
right.
I'm wondering if you could relate it to the sigmoid you mentioned here.
Sure. So, okay, in the tutorial you had, so you've seen that softmax is actually sort of the generalization of sigmoid for many classes. And for classification, we're going to talk about it in a while. For classification, we usually use softmax loss, like softmax with cross entropy, as you've learned, at the top of the network. So you can say again, you know, with some analogy to the meme that you're seeing now. So you can say that a softmax classifier with many layers is a neural network for classification. Okay. Are we good?
So the use of sigmoid just means we're in the case of binary classification?
Oh,
Like
this would be, yeah, sorry,
network.
I'll clarify this. This meme refers to putting the sigmoid at the end of the network. And this is not the same as having sigmoid activations inside the network for each neuron there. So you can have for each layer whatever activation you want to have, but the thing that determines the type of task that you're going to perform is more related to the activation that you will have at the end of your network. So if you have a sigmoid at the end of your network, then it would be, it can be good for many things, but it would be specifically also good for binary classification. Okay?
Okay, thank you.
Okay, so now we understand how the network is built. Okay, what is the function that the network represents, or at least the building blocks. But remember that what we want to do is to train this thing that we have now. We want this to be able to perform the tasks according to the data we have. And the way we're going to approach this is again by gradient descent. Okay, so let's try to think together what we need to do in order to train a network with gradient descent. So first, we need the label vector, right? We have the output vector and we need the label vector for each iteration of this gradient step. And we're going to have some kind of loss. And the loss is going to be a function of both the output and the label. And now let's see what we need to get. So to perform gradient descent, we need to know the derivative of the loss with respect to all the parameters that we have in our hypothesis. So the parameters we have in our hypothesis are all these so-called weights and all the biases that we have. So we need to have both of these for all L, I, and J. Okay, every weight that you see here. And in the past, when we were practicing linear regression, for example, or a softmax classification, this was sort of an easy task because we had this analytic expression of the loss with respect to the weights and the inputs. So let's try to come up with something similar in our case, okay? So here is, for example, if we take our we look at the last layer and note that I don't use here the activation function because it's actually pretty common for the last layer not to have any activation, to have it linear. Okay, so now I can express the output with respect. I'm taking just the rule that we just learned, and I'm able to express the output. Each neuron of the output vector, I'm able to express it with respect to the neurons of the layer L-1, capital L -1. But I only have here the weights and the bias of the last layer over here. Okay, so let's try to open it up and to have more parameters. So the thing is that every neuron that we have in this L-1 layer can also be expressed just by this building block, this neuron function, as a function of the neurons that we had at the layer L-2, right?
Assaf?
Yeah.
Shouldn't the B here have a superscript of L of the layer it belongs to?
Yeah, it should. Yeah, I'm sorry for that. Yeah.
Okay, thanks.
And the WL, shouldn't it be JI instead of IJ, or am I missing notation?
Yeah, you're right again. Yep. I should say that I make many mistakes, and it's okay. Feel free to correct me. Yeah, but you're right. This should be JI. The thing is, I didn't decide until the last minute if I'm going to do this with the transpose or without it. So some traces left. Okay. Okay. Sorry for that. Yeah. Okay. So now we can look at this L-2, and I guess that you can by now you understand what's going to happen. So we're just going more and more, and we're going to have this gigantic function. And if we have many layers, and neural networks these days can have hundreds of layers, and we're going to have a very complicated function. And if you want to have the derivative with respect to some weight, you know, here at the very early layer, then you're going to have to make tons of calculations, and it's going to be not practical at all. So this is the problem that we're facing if we want to train a neural network using stochastic gradient descent. So what we need to do is to use an algorithm called backpropagation. Okay, and for the backpropagation algorithm, let's look together at a couple of observations that are going to help us. Okay, so again, I apologize that in some of these calculations you're going to see ij where it should have been ji. Okay, sorry for that. So here we have our expression for a single neuron, and let me just add another annotation that's going to help us. And the linear process, just before applying the nonlinear activation, I'm going to name it z. Okay, so x is sigma of z. We're going to use it later. Okay, and let's look at what we want to get. So, for example, for all the weights, so we want to be to have the derivative of our loss with respect to each one of the weights. So one thing that we can do is just use derivatives chain law. Okay, so using the chain rule, I can say that every weight that I have, I can just say that I can express the derivative so that it's going to be L to X, the neuron that is connected at the pin point of the arrow of this weight, X, L, J, okay? And multiplied by the derivative of this neuron with respect to the weight. Okay? Yeah.
Do you mean by DL by DZ, JL, or by DX?
So, sorry, what?
Shouldn't there be the derivative with respect to Z, JL?
No, we don't have, no, I don't have Z yet. Look what we have here.
Sorry.
I have the derivative of the loss with respect to a neuron multiplied by the derivative of the neuron with respect to the weight. Okay? This is just a very simple split I'm going to do. But there is a reason why I'm doing this. And the reason is that this is a very complicated calculation for me. I don't know how to do this calculation. So I'm trying to reduce the problem. And I'm trying to reduce the problem to two elements that I know how to solve. So, okay, so I wanted to ask you that. So can you help me, please, if you haven't seen yet? Can you help me, please, and to find what is this expression over here? So I claim this is a very easy calculation. Can anyone help me with that?
It's the derivative of the activation function at z multiplied by the x's in the just the x's in the same xi sub l minus 1.
So I'm guessing what you're saying is correct, but let's just clarify that it's just one x, okay? Because this, if I have the derivative of some neuron with respect to a specific weight, so it's all going to be just zeros, except only the relevant neuron, the one that's connected to it through this weight. So this is a very easy thing, and keep in mind that we're going to discuss this, but this is very easy. And let me just explain how easy it is. So what we have here is just x, the value of some neuron multiplied by this thing that may look at first glance may look complicated, but it's actually really easy, because if you think of what it means, the derivative of activation functions. So for the common ones, it's super easy. So you can prove it by yourself. It's really easy to show. For example, for sigmoid, there's a very simple formula. And if you look at ReLU, which is the most common one, it's actually going to be embarrassingly simple because for a ReLU, the derivative eventually is just going to be either multiplied by 1 or multiplied by 0. Okay, so in some cases you're just going to say that everything is 0, you're going to kill it, and in other cases you're just going to leave it just the same as it is, and this depends on the value of x or the value of z, if you want. So we know this is easy, and now we are able to reduce our problem to just this expression. So instead of looking for the gradient with respect to all the weights and biases in the network, we are now able to just look for the gradient with respect to all the neurons that we have in the network. And the gradient or the derivative with respect to each such neuron, we're going to annotate by G superscript L subscript J, okay? And the process that we refer to as backpropagation is meant to solve exactly this. Okay, so we aim it for exactly finding G. So let's see how it works. So we have here at the bottom, again, the equation that expresses the value of each neuron that we have. And you can see that in the network that you have now, so for each neuron, we have two values. We have the X value, which is the true value, the forward value of this neuron. But each such neuron also have a G value. And the G value is what we want to obtain now. Because remember where we're standing, if we have all the G's, we have the derivatives with respect to all the neurons, and then it's very easy to obtain the derivatives with respect to all the weights. All right, so remember that G is DL to DX, LJ, okay? And let's look what that means, okay? We wanted this derivative, okay? DL to DX, this is what we're looking for. And what I'm going to do now is just split it open, and I'm going to use just a simple chain rule for full derivative. So I'm guessing that most of you know, or all of you know, that, for example, let me just state it quickly. If you have some function, say f of a and b, where a is a function of x and b is a function of x, then if you want the derivative of f with respect to x, then it's going to simply be the derivative of a to x plus, sorry, it's going to be the derivative of f to a multiplied by the derivative of the a to x plus the derivative of f to b multiplied by the derivative of b to x, right? I believe most of you are aware of this. This is just a simple chain rule, and we're going to use it in a very wide range. So the summation that you can see here, okay, what it actually says, let me clear up all this mess I did. So what it actually means is that we're going to sum over the derivatives one layer forward and then multiply the relevant weight and multiply the relevant derivative of each neuron according to the neurons before. So this is what we're actually doing. So we just split this direct red arrow to these three arrows and then these more three arrows. Okay, is this clear by now? Is this split okay? Everybody's with me? Are we good? Okay, this is just chain rule, right? Now, please help me.
I have a question actually about the index of G in the slide.
Okay.
Is it correct? Like it's GK and then on top of that it's G0?
Yeah, you see, you mean here?
Yeah.
You see the three dots here?
No, like you see GZ. I'm just wondering if the indexes are right because I'm confused. It's G0 to the L plus 1, and then below that is GK to the L plus 1. Maybe you can explain the indices of G again.
So, okay, so G has indices just as the X, right? So you have, so the superscript says the number of the layer, and then, oh, you mean the 0 here? This was supposed to be 1. Sorry. Yeah.
Okay.
Yeah. Sorry.
Also
sorry.
the
Thank you.
Yeah.
The X index.
Okay. So and now, okay, now we have this split, and maybe you can help me again and tell me what do you see here? You have this derivative of xkl plus 1 to xjl. Okay. So what can I do with this expression? Can anyone help?
It's kind of the same as before, just replacing the rows of the W's and the X's.
Right. So it's actually very simple. It's just taking the relevant, this relevant weight that connects these two, you see, going from GL plus 1K to GLJ is actually just taking the relevant weight and multiply it by the derivative of the activation function at the relevant spot. And please remember again that in the case of ReLU, for example, this complicated thing you see here can either be just 0 or 1. So it's very not complicated. And the second question I'm about to ask you is, what do you see here?
GK of L plus 1.
Exactly. So you see that what we have now is we just went back to the same expression that we had, just with different index, right? So we were able now to connect G of L, J, with G, K, L plus 1, okay? And as you can probably figure out, this is a sort of a recursive connection. So we're now able to express G using the using G's from the layer that was one step closer to the output. And what does every recursion need? Every recursive mechanism, what does it need to be effective?
Base
Case.
A base case or a stopping criterion. And in our case, it's actually very simple, because the stopping criterion is something that we already know. It's the derivative of the loss with respect to the output layer, which is super simple because, for example, if we're using classification, then it's going to be just cross entropy with softmax that you just did in your homework. And if it's going to be linear regression, then this is exactly what we did 2 weeks ago. And so this is just the derivative of a linear process that we're actually, we actually already know how to do. So you can start by this, and then you're able to calculate G's for the entire network. So, so if we look at it now in a vectorized way, let's see one very important observation. So we can vectorize the final expression that we get, and we can do it this way. We can say that the vector of G's is now the matrix W transposed this time, even though I've made many typos before, and it's now supposed to be transposed, okay? And multiplied not by just the G values of the layer L plus 1, but we have this, you see this derivative of the activation. So I'm going to make a vector of these derivatives, and I'm going to multiply it pointwise. Okay, so this is very simple. You can think of it as a diagonal matrix if you prefer, or just a pointwise multiplication. Just each G values is multiplied by the relevant derivative of the activation. And let me ask you this. Does this structure look in any way familiar to you, to any of you? Like something we've seen a few minutes ago, maybe? What do you say? We have this vector, we multiply by a matrix. Okay, then we do it again and again. Any idea here? Okay, I'll try to help. Yeah, so
Is
someone?
the way we calculate just like the activation itself?
Yes, so when we apply the neural network, just in the beginning of this class, okay, we just learned how the vectorized process looks like, and you can see that there are some differences, but I'm not sure how excited you are right now, but this is super exciting because what we're now seeing is that calculating the gradients of the neurons of the network is actually equivalent to applying a neural network, just do it top bottom, okay? Or doing from the output to the direction of the input. So you can see that while activating a regular neural network or activating a neural network regularly is x super L as a function of x super L minus 1. And here we have GL as a function of GL plus 1. And the process is actually very similar because we have only several differences. So one important difference is that we have no activation. So calculating the gradients with respect to the neurons is actually a linear process. We don't have an activation. Second, we use we need to transpose all the weight matrices, and this makes sense, right? Because you can't multiply them otherwise. Third, we need to multiply by the derivative of the activation, right? All the neurons before we apply the weight to them. And lastly, we have no bias. But this is sort of exciting because now we can see that for learning in neural networks, and we're going to have a break in 2 minutes in case you feel like you need it. So when you learn in neural networks, basically what you need to do is to apply the network in a forward pass, and then apply it again with some minor modifications from the end to the start, and then you can get the gradients. So let's summarize this algorithm. So first you need to initialize your weights randomly, all the weights. Now you're going to repeat the iterative process of gradient descent until convergence. So first you sample a batch from your data. So you can see that we ungrade here the X here and the Y here. Okay, so we have our data and now we're going to activate the network. So step 2 basically says, do this feed forward, and you can see that now we have all the X values in the network and we finally have the value of the loss. Okay, so we have the X values and the loss. Now we need the G values. Okay, so we're going to do the thing that is called the backward pass. And the backward pass is actually very simple. Okay, so we start from the derivative of the loss with respect to the output. This is like the base case, the first step. And then we just use this formula of applying the weights, the weight matrices one after another, and also multiplying by this derivative over here. But we do this back propagation. We go to the back and we calculate the derivatives with respect to all the neurons. After we have these derivatives with respect to the neurons, now we need to translate them to have derivatives with respect to all the weights and biases. Okay, so we just do this calculation, which is super easy. We just multiply each to get each derivative. We multiply each G value that we have. Okay, with this expression that we had before. And lastly, we need to update our weights. Okay, so we use the rule of gradient descent. We need to have a hyperparameter alpha, the learning rate, multiplied by this the gradient that we have with respect to the weight, and then we update the value of the weight. Okay, and this is a backpropagation. Okay, this is how you train a neural network. Okay, so let's have a short break. Okay, let's do it an 11 minutes break so that we'll continue at 10:15. Okay, and then we're going to further generalize this this backpropagation process. Okay, so see you in a few minutes.
אתם רוצים לעשות פוז להקלטה?
כן. Okay. Yes, sure.
Yeah, in the fourth step, you wrote that the derivative of loss with respect to the, for example.
Yeah, you should this value should be multiplied by G. Is that?
Yes, and okay, that was my first question. And the second one, in the vectorized form, will this be a matrix? I mean, the expression you wrote xi l minus 1 times the activation, the derivative of the.
At which step you're now referring to?
At the fourth step, if we want to write it in the vectorized form, if we want to multiply our gradients of the layer L, so if we want to multiply GL times the remaining expression, this remaining expression will be a matrix.
Yeah, I mean, you can. So you can do it by a diagonal matrix, right? Because you have your okay. So you have the G values, and then you want to get the derivative with respect to each such W. Then yeah, sure, you can do it. You can vectorize it and to have it as a matrix multiplication. Yeah.
So I should just put it on the diagonal of the matrix and multiply it by.
Yeah, it's easy. I mean, I don't want to calculate it in my head right now, but it's easy to make it a matrix out of it and do this calculation. Yeah.
Assaf?
Right. Yeah.
I have a question. Why did we calculate the backward pass if we don't use it in any calculation of the weights or the bias?
Sorry, what we're not using?
You calculated the GL and G.
Yeah, so I just mentioned that in step number 4, okay, there is another mistake here. Each of these should be multiplied by the relevant G, okay? Okay, this is multiplied by the vector G, L, J, G, L, J. Okay?
Okay.
Sorry for that. Yeah. Okay, and so this is what we've just seen is the way to perform backpropagation for what we sometimes refer to as a vanilla neural network. So it has very specific kinds of layers that we got ourselves familiar with. But at some point, people started doing more things with the neural networks. And Jan LeCun is one of the most important figures in this field of deep learning. And he had this post and he said, deep learning at mort viva differentiable programming. And unfortunately, that didn't catch. So people are still saying deep learning and no one says differentiable programming. But he had a point. And his point was that at some point in time, people stopped just using this matrix multiplication and then activation and started doing this really crazy, wonderful things inside a neural network. And as long as you can perform backpropagation through it, you can use it inside a neural network. So this was his point. And for this sake, we need to generalize our process of backpropagation and neural network training to be able to apply to many other elements that we want to have inside the neural network. So now we're going to have these elements inside the network, and these can be vectors, these can be tensors, Okay, this can be whatever you want it to be. There are many types of inputs to neural networks, and each of them is going to have this sort of vectorized value, but it's also going to have its gradient value. Okay, so each such element has its forward value. We're going to just annotate it without anything, and then the point G says its gradient. And we want to be able to have any transformation. So just a general T, doesn't have to be linear, doesn't have to be anything, and to be able to apply it to this X. So we apply this and we get the X of the X value of the next layer. But each such transformation has its parameters. It can have many parameters. So this linear transformation that we know of has this one matrix of weights, but all sorts of transformations can have many types of parameters that are also used when we want to produce the output of this transformation. So if you look here, the transformation is a function of XL, but also uses all the parameters that belong to this layer, and these are the learned parameters. Okay, now we need to backpropagate such things. So it means every parameter that we have for this layer also has its gradient that we're going to use to optimize our network. And we know that each such gradient is going to be the derivative of the loss with respect to, sorry, this is supposed to be X, with respect, sorry, this is supposed to be W, okay, to this weight. And sorry for all these F's here, okay. And but the basic idea, okay, this was supposed to, these F's here are supposed to be X. Okay, I'm sorry for that. I'm going to do this. Okay, this X. I changed some of the annotations in the last minute. Okay, and probably missed that. Okay, so when we have the gradient with respect, we want the gradient of the loss with respect to this X over here. So we can again split it as we did before, and we say that this can be the gradient with respect to X1 multiplied by the gradient of X1 with respect to X0. We just use the simple chain rule, okay? But to generalize it further, we're going to say that when we did the transition from X0 to X1, we didn't just use the T1 transformation, we split the transformation to two methods. So we're going to have a forward method, and we indicate here that this process is the forward method, but we're also going to have a backward method, okay? So the backward method is defined so that it returns the gradient of XL when given the gradient of XL plus 1. So the same way the forward function propagates forward the values of these tensors or neurons or whatever, so the same way the backward function backpropagates the gradients. Okay, so it receives as input, it gets this gradient of X1, and then the backward is applied to it, and so that we're able to get the gradient of X. However, you should also note that what we're finally interested in is the gradient of the parameters. Okay, this is just a tool for us. Okay, so we can define the backward function in this way. Let me do this way. So that the backward function not only returns the value of the gradient of the layer that was before, it also returns the gradients of all the parameters. Okay, so this is how we're going to define it. Okay, so let's see it more in context. So let's say that this is the network that we have. Okay, now let's follow the process. All we have now is the input value X. We feed it to the transformation T, but the transformation T also requires its parameters. Okay, this thing is called the computational graph. Okay, so we feed x super 0 and w, and now we can activate the forward method. Okay, and we get the value x1, and the same deal goes here. We can feed x1 and w. Now we do another forward. Okay, again and again. Okay, and all the way until we can get this output over here. Okay, and now I have the last layer is the loss layer, and note that the loss layer doesn't have any parameters. Okay, it applied without parameters, but what it does need is the label y. Okay, so given our output x superscript capital L and y, the loss function now is applied, and we get our loss value. Okay, so what we had until now, this was the forward pass. Okay, now we want to do the backward pass. Okay, so we take the loss and we take the derivative of the loss with respect to XL. This is what happens behind the scenes, but what really programmatically happens is we just use the backward method of the loss function, and now to be able to get XL point G, this is the gradient of this output layer. Now we can just go on and on. Okay, we apply the backward. Okay, and the backward function gives us both the gradient with respect to the weight, but also the gradient with respect to this input layer here. And then we go on, apply backward, we get this, we get that, apply it again, backward. Okay, and this is how we generally train a neural network, and we can be very creative and have many types of layers here. So this is a very general way of performing backpropagation, and not specific to having these neurons. And so remember what you need to have to be able to perform this process is to have this set of transformations, set of layers, and each one should have a forward method and a backward method. And also every parameter and every neuron that you have in your network must have these two elements, this forward value and gradient value. This is apparent also when you will be using, for example, PyTorch. Okay, so this is a programmatic generic way to do this, and you can think about this. You can be very creative. This T1 that you see here, it can be many things that you would want to apply. After you did this, now you can update your weights using this gradient descent rule. By using reducing subtracting the derivative value multiplied by the learning rate.
Assaf?
Yeah.
Is there any use for x0, the gradient of x0 in this case?
Great question. Usually no. At some interesting applications, there is some use, and so in a few classes you'll see some applications where you want to actually change the pixels of an input image so that it matches something that you want to do, for example. Okay, or adversarial examples is a thing that we're going to learn. But usually, like for traditional tasks with the neural networks, then no, you're not going to use this. So let's see a nice example, a simple example, and just what I want to express here to you is that what the types of layers that we've seen before are special cases of the general way we're looking at it now. Okay, so for example, if you have this layer that consisted of a matrix multiplication and then an activation, so the most general way is to look at it as two separate layers, so that we have the ReLU layer that has its own forward and backward, and we have the linear layer. It only has one matrix of parameters and it has its own forward and backward, right? And you're going to do these things in your homework, but it's very easy to see, right, that we know how to apply ReLU to a vector. So forward is easy, and we've seen that backward is actually the multiplying by the derivative of ReLU. So this backward function here is super simple. It's just multiplying by either 1 or 0, right? And we know that when calculating the gradient of a linear function is just taking the transpose of this matrix. So everything to get this, and you know, and we'll already see how to calculate the derivative with respect to the parameters themselves. So it's really actually super easy to do. And by the way, you can actually backprop through any directed acyclic graph. So you can actually, you don't need to have this sequence of layers. You can do whatever crazy things you want to do, and people do this stuff. You'll see a thing called ResNet, for example, in the near future, and you can see, for example, that there is no problem doing this thing called skip connection that you see here. So you just have this layer, which is this summation layer that gets 2 inputs. So it gets this input here, and it gets this layer from here. Okay, and it's actually very simple, because all you have to say is, okay, so forward is easy. You take this plus this, and backward is also very easy, because what you need to do is just to say that the backward function needs to have several outputs, and it needs to return outputs of the derivative both with respect to this input and both with respect to that input. And if you have others, then it's also possible. It's not a problem. And specifically, you know, summation is a very easy process to differentiate, right? So the gradient is with respect to each of them, you just have the sum of the gradients. So you can be very creative and do whatever you want with this stuff, as long as you have a directed acyclic graph. Then you can do backpropagation through it. So we're almost, yeah.
Just to make sure I understand. So before, when we first encountered this example, so the linear stage and the ReLU stage were represented as one operation.
Yeah, exactly. And we learned only to, you know, very specific way. We learned how to backpropagate through a sequence of linear activation. Okay, and now we're saying you can do whatever you want. Okay, you can be as creative as you want to be. Okay. All right. So we're almost finishing here. Oh yeah, a few more things. Yeah. So here's a question to you. So what do you think would the terms be for a function to be inside a neural network? So can we use any function inside a network? What would you say? What can be the limitations for it? Any ideas here?
Differentiable functions.
Right. So the first thing, it has to be differentiable, right? Because otherwise we can't manage it. I should say that there are some solutions to functions that are almost differentiable, or things that you can cheat in some cases, but generally it has to be differentiable. And so this is an easy observation, but there is one more thing that maybe that should be considered. It's not enough to be differentiable. We should always consider the implications to the optimization process. And this means it has to be, we call it stably differentiable and reasonably differentiable. And there are many other things that we can't just put simple rules, but when we use them, we can see some effects on the optimization process. And I'll just give 2 examples. Let's say that I have some task that I'm performing, and I know that the output I want, this is a regression task, and I want the output to be between 0 and 1. And I want the loss of this network to judge it so that it will always, always be between 0 and 1, and then it will be judged. So at the end of my network, I do a function that does clamping. If it's bigger than 1, return 1. If it's smaller than 0, return 0. Otherwise, return the exact value. Does anyone see any problem with this approach? Any ideas? Why can this be problematic?
Vanishing gradient.
So I heard vanishing gradients, and the gradient indeed vanishes, but vanishing gradients is a phenomenon that usually is attributed to another thing. It's true that the gradient vanishes, and I'll explain why. Because if I put this function at the end of my network, so we can see together that, let's say I get an output that is bigger than 1. Okay, so this is the value I get 2. Okay, and now I need to take the derivative with respect to one layer before. Unfortunately, what is the derivative here? Can anyone tell me? So yeah, so it's showing me the derivative is 0. The gradient is going to be then 0. And now that the gradient is 0, it means that my network is not going anywhere. If I have a gradient of 0, then nothing is going to change. Everything is going to stay frozen, and my network is never going to train. It's only going to train if by random, by accident, I get values that are in this place. But anytime I'll get a value bigger than 1 or smaller than 0, then nothing is going to happen, and the entire learning process is stuck. Okay, any ideas how would you solve such a problem? You say you want values that are restricted between 0 and 1. Any ideas?
You can shift a hyperbolic tangent upwards to be.
Yeah, you can shift a hyperbolic tangent upwards, and then you will get what we call a sigmoid, right?
Okay.
A sigmoid is exactly a shifted hyperbolic tangent. Yeah, so we can use a sigmoid there. I want to give you another example. So what if I want to use, and this is a thing that in other disciplines can sometimes used to get to encourage output to be sparse. Okay, what if I want to use an L-half norm, so that the loss of my network is going to be a square root of something. Does anyone recognize any problem in this case?
I don't know if it's a problem, but it's non-convex.
It's non-convex, but you can still, I mean, okay. The non-convexity is actually, it does influence, but the most, I would say the intuitive way to look at it, if we look at the function of a square root and say we have just one scalar output, and now we're going to do gradient descent. So it's not 0 anymore, everything may look okay. But look at this problem here. We're performing gradient descent. So let's say we're at this point, and then we're at that point. Then the thing is that the more we are closer to the to have a loss of to have a small value for the loss, we'll say this, the gradient is heading towards infinity. So even if you have like this in L-half norm, it looks actually like this. Even if you have it, you know, in this way, you're going to have very high values for the gradient. So probably your gradient will just jump from side to side, and there's no chance that you'll be able to get a low value. This is very unstable. Usually you don't want high gradient values that you want to get. So these are just two examples, and you can't really set up, at least not where research stands today, exact rules for what you can and cannot use to be effective. And the reason for this is that the entire optimization of a neural network is actually sort of a magic. No one brought it up. I thought someone would, but remember that the function of a neural network is highly non-convex. Nevertheless, we are able to optimize it. So we're not going to talk about this. Sort of is the holy grail of of theoretic research of optimization in neural networks, and we're not going to cover this now, but this just suggests that there are many things that you can do in a neural network that may be problematic, that you may find out later that are hurting your optimization process. So just before we finish, I want to show you one thing.
Assaf, can I have a question?
Yeah, sure.
In the first example that you showed, you said that there's a problem of the gradient, right? But the most used function today is ReLU, and it suffers from the same problem, no?
No, no, because the thing about ReLUs is, okay, so when you have a ReLU activation, not at the end of the network, you have somewhere in the network, it means that if you have a positive value, then you're going to have a gradient with that is not zero. If you had a negative value, and this neuron is eventually zero, then also the gradient is going to be zero. So what's going to happen is that at some neurons, at some cases, are going to be sometimes positive and sometimes negative. And they're only, and the weights that are connected to each neuron, they're going to change only at these iterations where the neuron was eventually turned up to be positive. In iterations when this neuron is negative, or not the neuron, the Z is negative, and then the ReLU turns it to zero, then you get no gradient for these through these weights. Okay, but you also have to keep in mind that all the neurons in the layer that is behind it, okay, they're all connected to other neurons. So it doesn't mean that you have this block that nothing is going to flow to the back. Okay, it's not like a bottleneck. Okay, there's still gradients going to flow to the back of the network. Just this specific weight that is connected to this neuron is going to get a gradient of zero for this specific iteration. Okay?
Yeah, thanks.
Okay. I want to mention one quick thing, that there is a really great blog post that I like for many years. It's almost 5 years old, by Andrei Karpathy. It's called "Yes, You Should Understand Backprop." And it has nice examples and for phenomenon that you may encounter when training networks, things called dead ReLUs and stuff like this. And this is super interesting, even though it's 5 years old by now. And I just want to, for some intuition, to play with the neural network. And so I want to show you this. This is a JavaScript by TensorFlow. Let's, 1 second. Okay. All right. So what I want to show you here, I'm using this playground, and it's really super cool. You can add it's a toy example. You can add layers, and you can choose learning rate and stuff like this. And I want to show you a few examples. So the way it works, we're going to perform classification. It uses a binary classification with logistic regression. And you can see that the colors are the logistic regression probability. So between class -1 and class 1. And you can see the training data of 1 and -1 with the green and blue. So this is a very easy case. And look at what I'm training now. I have 0 hidden layers. So I hope you all remember that having 0 hidden layers is just simple logistic regression in this case. And very fast, the training happens very fast, and you can see how the probabilities work, and the boundary line is right here in the middle, and it looks quite good. However, if I go to a more complicated problem, what if I go to a data that looks like this? So as you can imagine, there is no good linear solution for it. So this is really very bad solution. But let's try and add more layers. So I'll have this 1 hidden layers with 4 neurons, and let's see what happens now. And you can see it gets a little better, trying to isolate these data instances in the middle. Let's add 1 more layer. And now you can see how beautifully it trains to capture these. And the more layers I add, it can be more complicated and smooth function. Okay, whatever. And pretty fast be able to do this classification. And let's look at a much more complicated example. So this is a super hard example, this spiral structure. And of course, if I have like one hidden layer, then it's not going to work very well. It can try, it can. But if I have some more layers, let's try this, and some more neurons. Then now we can see it slowly optimizing. Okay, everybody's seeing it well, right? We're good. Okay, so just give it a little time while it's optimizing. And I want to point out first intuition regarding the representations. So you can see that each layer in the network we have just is simply linear and then ReLU. So if you look at the first layer, so each such layer, if I put my cursor on it, then you can see what this layer does. Okay, what is the values that it gives to any X, Y values here. And you can see that all the neurons of the first layer, they are basically just splitting the data in two, and they give the value of and they give positive value to half of them and zero value to the other, because they are just linear and then ReLU. So this is what they're able to do. So the first layer does a very non-complicated action, a very simple action to perform. Now the advantage that the second layer has is that it also does a very simple action, just linear and ReLU. But the difference is the input to the layer. The features that it is now activated on are not just the X1 and X2, but the first layer applied to them. So it has these many angles here that it can use, weighting them linearly and applying a ReLU. So for example, it can do this, this circular shape over here, almost circular shape over here. So this is what this neuron does. So now we have a much more complicated representation of the data here. And the representation of the data goes on, and the deeper we go through our network, so does the representation becomes more complicated, and until the final classification that we have that can be very expressive using the fact. But you have to remember, you can see, look at the last layer here. This scalar that we're now getting for the classification, okay, a scalar between -1 and 1 that we get here at the end is nothing but linear weighting, okay, but a linear action performed on data. It just so happens that the data that this linear action is applied to is this very useful representation that we have here in the almost last layer, okay, this thing that we have now. And this is what I mean when I say that the greatness of neural network is representation learning, okay? We'll learn how to represent the data so that a simple linear action can do really great things. And this will go on and be gradually more impressive as we can do this to images and videos and recognize very complicated concepts using this idea of hierarchical representation. So, okay, we're now really finishing. So I hope that this topic of neural networks and like introduction to deep learning was somewhat demystified for you. You're going to implement all this stuff in your homework, and I just want to say that this week's tutorial, so Shir Amir is going to give it, and it's going to be an intro to PyTorch. So we're going to take the concepts that we just theoretically learned and now do this programmatically using PyTorch, forward, backward, gradients, everything vectorized processes. She will show you everything. And then next week, unfortunately, you're going to see me again, and we're going to talk on one of the most important variants of neural networks, which is called convolutional neural networks. This is the type of neural networks which we're going to use, I guess, for almost all of the course and almost all the tasks in computer vision. This is the type of network that is used. Okay, so that's it. One comment before we finish. We had many typos regarding transpose of matrices. So one thing I'm going to fix it and then reload the presentation with all these transpose things fixed. And the second thing is that don't be afraid of it, because when you implement such things, if you're wrong with the transpose of the matrix, then simply you're going to get an error, because this is going to be a non-legal operation. You can't multiply a vector with the wrong sized matrix. So it's very natural, fixed by itself. And that's it for today. Next time, Shir, then me again on convolutional neural networks. I want to thank everybody for listening to me, and thank you for being with us, and we'll see you next time. Thanks.
Thank you, Assaf.
Thank you.
Yeah. So if you have questions, I can stay for a while. I'll just close the recording 1 second.